Hello. Hi, and in this video, we'll be learning how can we perform delete operation and min-max operation in binary search tree. So this is part 2 of operations in binary search tree, where we'll be doing these delete and min-max operation. So these two are very important operation, and especially the most important operation is the delete operation because it's a little bit more complex than the previous operations which we have covered before. So we'll be completing that. We'll be learning about the delete operation in binary search trees. So if you haven't watched the previous videos, please watch that so you'll get a better understanding of what trees are and how are we performing traversals in order, post order, that is BFS and DFS. Okay, so you will see that. So please watch the previous videos if you haven't. So if you want to know where is the playlist available, you can simply visit the channel Geeks for Geeks Development. And here you can see that we are live. So in the playlist section, you'll find the playlist for data structures using JavaScript. So you'll see that these much of topics have been covered, and the main thing which is required for this specific video is knowledge of trees. So you can watch this video and binary search tree. Then you can watch part 1 of operations in BST, that is here. Okay, this one is actually here. And then you can also watch the difference between BFS and DFS, which I have taught here. Okay, so you can follow these 3 videos at least before watching this, because this is very important video. Okay, so now what we'll do is, okay, first of all, I'm going to explain you what is actually min-max, and then using min-max, actually minimum will be used. We'll be using min-max for delete operation in trees. Okay, so let's begin. So before moving on, in the live chat you can see that we have a course provided by Geeks for Geeks. So if you visit that link, or you can simply visit the description and you'll find the same link of a course. So if you visit that link, it takes you to this page. So it is a paid course by Geeks for Geeks for data structures and algorithms in JavaScript. So those of you who are interested to learn this from beginner to advanced level can check out this one. And here are all the contents which are covered in this one. So everything is covered actually. So if you are opting for web development or computer programming in DSA using JavaScript or any other language, these concepts are always used. Okay, these concepts are always used. So you can check out this one. Okay, so now we can continue. So first of all, I will explain you the concept of min-max. All right, Chandan Pandey, operation on string. Uh, are you demanding for a specific video for operations on string? All right, so what I'll do is I'll just open whiteboard so that we can draw things here. Yep, fine. Request for operations on string. Yeah, definitely. We'll try to bring more videos on that. Specifically, I thought that I would be teaching strings in this specific series, but actually string is not a data structure, it's a data type. So I thought that I won't include it in this playlist. But if you want me to include strings also, I'll definitely include that, because strings also play a very major role in JavaScript, and also asked a lot in competitive programming also. So but I thought that for this specific course it won't be much fruitful, so that's why I didn't include it. But yeah, definitely we'll be bringing specific video for operations on string, and what are actually different kinds of things which we can do with strings in JavaScript. All right, so now what I'll do is I'll just open yesterday's drawings, and yeah, it's here. So we were actually referring this diagram yesterday. Okay, this one, you can see what happened. Okay, just a minute. Hmm. Fine. Also, guys, if you have any doubts or you are requesting for some videos, you can definitely message me on the live chat. Okay, I'll answer all your queries, and sometimes I might take some time to give answers for your queries because I might be busy doing the explanation and doing different works. Okay, so please wait patiently and just mention your doubts in the live chat and just wait for a while. I'll answer them. Okay, so yeah, we were actually referring this example. So if I talk about a minimum value of this example, what will be the minimum value? Obviously 5 will be the minimum value, right? And what will be the maximum value? 17 will be the maximum value. So from observation of BST, I'm talking about binary search trees, you can simply say whatever element is on the leftmost side is the minimum, right? And whatever element is on the rightmost side is the maximum, right? So that's how you can actually know what is the minimum and what is the maximum. Okay, so for finding that, I can simply start with the root node. Okay, I can simply start with the root node, and what I'll do is I'll just copy this diagram. Okay, I think this will work. Okay, I'm just assuming that this is working. Okay, so what I'll do is I'll just paste it here. Okay, fine, good. So we have copied it successfully. So let's do one thing. Let me just make it cleaner. Yeah, fine. Okay, so this was the example which we were referring to yesterday. So here you can simply see that we actually have some values here. Okay, so you all know that this is actually the min value. Okay, this is going to be the min value, and this is 17, that is rightmost side is always going to be the max value for any binary search tree. Fine. So how can we actually visit the leftmost side? It's very easily. You will simply start with the root, okay, root node, and you look for the left child of the root node. Whatever is the left child, you go there. Again, you'll look for the left child again. Okay, left child, and it's like that. So you will visit the left side automatically, and that will be the minimum value. Similarly, we are looking for the maximum value, so we'll again go for the right side, and again right side, and again right side, and the last right side will actually won't be having any child, so that will be our maximum value. Okay, so where to stop? You have to stop in that node which does not have any right side. You can see it does not have any right side. Okay, that means it is the maximum value. Okay, I'm not talking about left side, I'm talking about right side. Okay, so it does not have any right side. Okay, it does not have any right child. That means we have to stop here. Okay, that means we have to stop here. And similar is for the left side. It does not have any left child. Okay, it does not have any left child. That's why we need to stop here. Okay, I'm not talking about the right child here, I'm only talking about the left child. If it does not have the right left child, we have to stop here. Okay, that means it's the leftmost value, and we are ended here. Okay, fine. So now we can continue with the coding part. So again, I'll just explain you what I did right now. So first of all, I'll say that go to 12. Okay, I'll be starting from the 12. Okay, again, I'll say I want to go to the extreme left side. So what I'll do is I'll go to the left side of 12, left child of 12, that is 7. I'll go to the left child of 7, that is 5. I'll go to the left child of 5, that is null. Okay, that is null. That means I have to stop, and I will simply return the root value, whatever is the root value. Okay, initially this will be the root value, right? Okay, we assume that this is the root value, but we will be changing the root value, and whatever is the last value will be returned. Okay, similarly, if I talk about the min, okay, if I talk about the min, it's here. If I talk about the max, max simply says that go on to the right end. Okay, that is we'll be going to the right side, that is 17. Okay, if I had any other right child of 17, I'll be going there, and it works like that. Okay, so till the end you will be visiting there. Okay, once you reach the null part, okay, you will be simply returning 17. Okay, whatever is the last value, you will be returning that. Okay, so this is actually the max value, and this is actually the min value, and you'll be finding things like that. Okay, so now we'll be writing code for that, so that you get a better understanding and practical implementation for the same logic. Okay, so let's open VS Code first. Yeah, fine. Okay, so you can see that we were actually working on this one, and what I'll do is you can see that in the last few videos we have covered a few operations here. Okay, first one was what? Insert, and then we perform different operation like pre-order, traversal, post-order, in order, and then we have performed the level order, or you can call it as BFS traversal. Okay, so we also performed this in the last video, and now you can see that below I have actually called the operations. I have actually called the operations and I have inserted values like this and so on. So please watch the last video so that you get a better idea for that. Okay, so now what we'll do is we need to find the min and max values. Okay, right? So for that we can simply find the min and max value by simply, first of all, we'll just declare these things. Okay, right? We'll just declare these things, so we can simply say min value. Okay, so for min value I'm just going to create a function named as min value here. Okay, that is, it's actually inside my tree. You can see tree class, it's actually inside my tree class. Okay, so it's inside the tree class. So here you will simply say that whatever is the root will come first. Okay, root, that is 12 will come first. Okay, so first of all I'll just say that if the root does not, that means have any value, if the root does not have any value, I'll simply return its value. Okay, I'll simply return null. That means if the tree is empty, I'll simply return the tree as null. Okay, that means I don't have any value, so I'll simply say if the tree does not have any value. Okay, does not have any value, that means it has null value. Okay, that means the tree is empty, so I'll simply return whatever is the value. That means obviously null will be there. Okay, null will be returned. But after this, if I talk about, if I have some values, okay, either left side or right side, so now we'll be actually working on the left side and right side. Okay, so now we'll be actually working on the left side and right side. What we'll do is uh, okay, so let's begin again. Okay, actually I wrote the wrong code. So here what do we need to do is I'll simply say that if what I told you was, if you talk about any tree, any specific tree, where do we need to stop? Okay, where do we need to stop? Like suppose 12 does not have any left side. Okay, if I talk about this 12, if suppose if I have a tree like this, okay, where I don't have any left side, okay, but I have a right side, something like this. Okay, I don't have any left side, that means left side is null. So can you tell me what's the minimum value of this tree? The minimum value of this tree is actually 12. Okay, minimum value of this tree is actually 12 because this tree does not have any left side. Okay, from the root does not have any left subtree. That means the minimum value is 10, is 12. Okay, fine. So we'll simply do that. We'll simply say that if my root, if whatever is my root, okay, you can actually check for the tree is empty or not again. Okay, you can simply return null and like that. But what I'll do is I'll say that if root dot left side, if I don't have left side for the tree, I'll simply return the root. That means my root is the minimum value. Okay, whatever is my root, whatever is the value, that means 12 is my minimum value. Okay, will be returned there. Okay, I hope you got this. And similarly, if I have the left side, what I'll do is I'll simply visit the left side. I'll simply say, again call this function recursively. So I'll just say this dot min value. And now what I'll do is I'll change my pointer from 12, 12 to 7. Okay, from 12 to 7. Suppose if I talk about any specific uh, 12, 7, 17, 5, 9. Okay, again I'll draw a tree so that you get a better idea. So simply, you know that simply you know that 12 had a left child. Okay, 12 had a left child. So what I'll do is I'll shift my pointer from this 12 root to 7 root. Okay, that means now root will become 7. Okay, I hope you got this. So inside this, I'll simply say whatever is the left value will now become my root. Okay, now will become my root. Again, this function will be called, I will check that whether 7 has any left child or not. 7 has a left child, right? 7 has a left child. So again, this will be called. And now what will be passed inside this? 5 will be passed inside this. Okay, again, this function will be called, okay, with value 5. Now 5 does not have any left side. 5 does not have any left side. So I'll simply return 5. That's it. It works like that. Okay, so I hope you got this. And similarly, we have the max value. Okay, max value. And it's the opposite of that. I'll simply say that, again, just copy this. You'll say that if it does not have the right side, if the root does not have the right side, that value, okay, I'm sorry, if the root does not have the right side, I'll simply say that whatever is the value will be simply returned. That means if I talk about this again, you can see in the same tree, suppose it does not have any right side, that means right side was null, right side was null. So it simply means that 12 is the maximum value, right? 12 is the maximum value. So I can simply say that whatever is the value will be simply returned. If the value does not have the right side, that value will be the maximum value, will be the final value. And similarly, if it has the right side, simply call this function recursively for the right side. That's it. So extreme right side will be provided. Okay, so suppose you reach 17, you'll simply call it for 12 first. Okay, you'll say that 12 has a right side, so this will be ignored, this will be called. Okay, so now 17 will be passed inside this. Okay, so again, max value 17 will be called. 17 does not have any right side, that means this statement is true. Okay, so I'll simply return 17. Okay, that's it. So that's how min and max work in this case. And so that's how min and max work in this case. Okay, so now similar logic, actually the min value is actually used in delete operation. Okay, we'll see how it is actually used in delete operations, but we'll be using this similar logic for delete. But yeah, delete is actually in parts, delete operation is actually in parts. So we'll be looking into different kind of scenarios which we'll face while performing a delete operation. Okay, so for that, what can we do is we'll simply again draw a diagram. Okay, so what I'll do is, I think I can paste it here. No, it does not work like that. Okay, let's just uh, copy it again. Okay, fine. So I'll just copy this again, and similarly I'll paste this tree somewhere. Okay, so now we are talking about the delete operation, right? We are talking about the delete operation. So how can we actually perform a delete operation? So it's a little bit complicated operation, definitely. Okay, so what I'll say is, first of all, before watching this delete operation part, please watch the previous videos completely, so that you will get a fast understanding of what's actually happening. Okay, so in delete we have actually got a few scenarios. Okay, we actually have a few scenarios. So suppose in this case, suppose I want to delete node 5. That means my first case can be that node, I want to delete that node which does not have any child. Okay, it's the easiest. So if I want to delete this node, okay, if I want to delete this node, okay, sorry. All right, so if I want to delete this node, so it's the easiest because it does not have any child. Okay, so I can simply just remove this part. Okay, I can simply just remove this part. That's it, very easily. I can simply just remove this part. And same is for this leaf, and same is for this leaf. They are the easiest because they didn't had any child. Okay, they didn't had any child. Okay, I hope you understood this. So first case will be this, we'll be deleting the leaf nodes. Okay, now if somebody, first of all, you need to obviously find the element. Suppose user will query that delete element 5, delete value 5. So I'll search 5 here, okay, then I'll stop at 5 and then I'll delete 5. Fine. Similarly, suppose if somebody wants to delete 9, so again I'll find 9 and I'm talking about leaf nodes, okay. I want to delete this 9, so 9 is a leaf node and it will be simply deleted easily like that, okay. We'll simply declare their values as null, that's it, okay. So that's how delete works in leaf nodes, okay. That means if the value user requested to delete was a leaf node, okay. Now we have actually a different scenario where your parent has one child, okay. So I'll give you another example. So I'll again draw this, okay. So we can do one thing. uh, if I just paste it here, okay, it's not like that. Fine. Yeah. So you can assume this as some other tree, okay. And for now, let's suppose that it does not have any left child. Let's say it does not have any left child. So what will actually happen is, you can see, suppose this was the tree, this was the tree, and now the user requests to delete 7, okay. If the user requests to delete 5, 9, 17, then this will be the first case, okay. This will be the case 1, leaf, okay, leaf node. But suppose I'm in the second case, so second case will be actually some parent node which has only one child, okay. Fine. So how to perform delete in this? It simply says that if your parent, that is if I talk about 17, has one child, if I talk about 7 has one child, so I'll simply do one thing. If I remove this, just remove this and shift 9 to its value, that's it. So what will actually happen is you will have 12, 9, and whatever is the remaining part of the tree, it's actually like that. So you'll remove 7 and 9 will take its value, okay. That's it. That's how it works for one child, okay. So that's how it works for the one child. But now suppose your tree had second child. Okay, so suppose now your tree had two childs. Okay, that means I want to delete something like a root node. Okay, what will happen is, so let me just uh, pick this again. Okay, suppose again, same case. Here you'll see, suppose the user now requests to delete 12. That means 12 had two childs, 7 or 17. Okay, 7 or 17. In this case, you can see 12 had two childs, 7 or 17. Okay, suppose this is the tree. So what we'll actually do is, we will find the right minimum, okay, whatever is the right minimum, and we'll simply change that, we'll simply shift that to 12, okay. 12 will be removed and whatever is the right minimum will be shifted. Okay, fine. So suppose now if I wanted to delete two childs, what will happen is, if I wanted to, sorry, if I wanted to delete the node which had two childs, so what will happen is, suppose if I want to delete 12, 17 will take its value because 17 is the right minimum, okay, right minimum, whatever is the right minimum will take the value, okay, will take the value, right minimum is 17, okay. Suppose we had some other case, something like, if I start from 12 and suppose I go from 7 and suppose I go from 7 to 5, again 5 to 9, and here what you have is, suppose the first element here is 17 and suppose you had, a few more elements, like suppose Here what I can say is having elements like it has 14. Okay, it has 14, and suppose it had 19 here. Okay, so I hope this tree, yeah, this tree is fine. So here you can see that this is some other tree. By the way, this is some other tree. So here you can see, suppose if I delete 12 again, if I delete 12 again, what must come here? 17 or 14? What must come here? 17 or 14? Obviously 14 will come here, so that binary tree won't be disturbed. Okay, so what I simply mean is the minimum element. If I delete 12, this 12 will actually be replaced by some value available on the right subtree, which is minimum. Okay, so minimum value of right subtree. Okay, right subtree, that means I'm still looking on the left side of the right subtree, but it's the right subtree. Okay, it's the right subtree, minimum value of right subtree. So again we'll be using min operation again here, and in this case it's actually 14, which equals 14. So now what will happen is, instead of 12, now we have 14 here. Okay, 14 will now become root. So the new tree is something like 14, and it's again 7, and it's again dot 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 and dot dot dot. It's like that. Okay, so now what will happen to 14? Now what will happen to 14? Same operation will be done. 14 will be deleted from its place. Again you will check, does 14 have any childs? First case will be followed. Okay, next, if 14 has one child will take its value. If the third case is there, that means 14 had two childs, then we'll repeat this thing. Okay, so I hope you got this, and these are the three types of delete operations which we perform in binary search trees. So now we'll see that by coding. Okay, okay, let me just give you a brief for this one also. So 12 7 5 9. Okay, so again we'll draw that. Okay, yeah, here fresh page, and here what I'll do is I'll say 12, and suppose I have elements like 7 5 9. Okay, this is the left side, and suppose the right side has child 17, and suppose in the left side I had again 14, and in the right side I had again uh 19. Okay, fine. So previously we were actually talking about, if I delete 12. Okay, if I delete 12, what will take 12's place? 14 will actually takes 12's place. Okay, 14 will take 12's place. Now 14 did not had any child. Okay, did not had any child, so we'll simply make it as null. Okay, simply make it as null. Fine. So this was the first case. Now if I talk about second case, what can be the second case? Again 12, I want to delete 12, but this time 14 suppose had a child, that is right child, that is 15. Okay, we'll say that suppose 14 had the right child, that is 15. Okay, so what will actually happen is, now you simply say that 14 has one child, 14 has one child. Okay, so suppose if I remove 12. Okay, if I remove 12, what must be the value which 12 can take? What must be the value which 12 can take? It's actually 14. Okay, it's actually 14, right? In this case it's actually 14, because it's the right minimum. You can see it's the minimum in the right. So again I'll just remove this also. Okay, so 14 will be passed here. Okay, 14 will be passed here. So now what will come in 14? 14 will be actually taken, will be actually changed to 15. Okay, so now what will happen is 15 will be taken, and actually 15 will come here, and now we'll simply make the child of 15 as null. Okay, this value will become null, because 15 did not had any child. Okay, it's like that, it's recursive. Okay, 15 did not had any child, so it became null. Okay, if it had one child, that child will take 15's value, and so on. Okay, so now you can see 14 had one child, and that is 15. 15 took its value, and now 15's value became null. Okay, old value became null. So again we have some other case. Okay, let's say we have some other case, and I'll just Control Z this time. Again you have this tree, but this time you have suppose one more child here, that is 13. Now just tell me what must happen here. This is a tricky question. So what will happen here is actually you can see, you first of all, first step is not to see for the child. First step is to see minimum value. So what is the minimum value? Minimum value this time is not 14, it's 13. Okay, it's 13. Some people do this mistake and I have committed a lot of mistakes in this case. Okay, so 13 will actually take the value of 12 this time. Okay, fine. I hope you got this. And 13 again did not had any child, so it will become null. This value will become null. Okay, so here you can again type that suppose again 13 will come here and this left side will become null. That's it. That's how you can perform delete operations. Okay, so I hope you got a clear understanding of all the possible scenarios. There can be actually, I think that we have covered all the possible scenarios, and you can assume this, you can draw this by creating more diagrams, because this is very important in competitive programming. So this understanding is very important. You can actually use pen paper, or you can use whiteboard to get a clear understanding how actually tree is working, how is tree performing operations. Then after understanding, you need to go to the coding part. You can easily understand the coding part very easily. Okay, some people just learn that, it's fine, but I would say first understand this. Okay, so now we'll be performing the delete operation by simply writing its code. Okay, simply writing its code. Fine. So what I'll do is I'll just start writing its code. I'll simply say, first of all, we have a function. We'll just name it as delete node. Okay, delete a node, any node, if you want to delete any node. So first of all, a function named as delete will be called. Okay, inside this I'll just pass whatever value has user requested. Okay, whatever value user has requested to delete, I'll just pass it. Okay, I'll just pass it. Okay, and now I'll simply update my tree. I'll simply update my tree by simply calling a different function by the starting root, that is 12, and the value is suppose the user wants to delete 7. Okay, so first of all we need to find 7 in this tree, right? We'll need to find 7 in this tree. If 7 is available, then we'll delete 7, and then we'll be performing those three different cases, whatever 7 fits in. Okay, I hope you got this. So what tree we are actually referring right now, we'll just assume that we are referring this tree. Okay, or we can actually refer the other trees which we have seen, but right now you can say that yeah, we are referring this tree. Okay, so suppose the user has requested for deletion of 5. Suppose the user has requested for deletion of 5. What will happen is the root value 12 of the tree, okay, and 5 will be provided to the function. Okay, will be provided to the function. You have 12 and value 5. Okay, whatever you want to delete, that's it. Now we have this delete node. We don't have this delete node function, so we'll be creating this delete node function. Okay, so delete node function will simply take two values which we have provided, the root. Okay, whatever is the root. In the first case, initially the root will be 12. Root will be 12, that means the starting point, and the value which we want to delete is 5. Okay, root 12, value 5. So now what will happen is, first of all we need to search for 5. Okay, we need to search for 5. So first of all, one more thing, if your tree is empty, you can actually, suppose if your tree is empty, you can actually return that yeah, my tree is empty, or you can return the null value. Okay, so you can simply say that if root equals null. Okay, then you can simply return null, or you can simply return root, whatever. Okay, same thing. Okay, so if root is null, you can simply return null, or you can simply return root, both are same. Okay, so here what I'll do is, after this I'll say that suppose I want to search for 5 in this tree. Okay, I want to search for 5 in this tree. Okay, what I'll check is if 5 is greater than or lesser than this 12. obviously lesser than, so I'll go to the left side. Again I'll check if 5 is less than 7 or not. It's less, so I'll again go to the left side. Okay, so now this time our value is equal to 5 and root is again equal to 5 because our pointer is on 5. So that means we have reached our value. That means we can perform operation. Okay, so here we'll be having three case. If root dot value is actually greater than the provided value, okay, that means 12 is greater than 5. Else, if suppose the user wanted to search for 17, suppose the users wanted to search for 17, now the root value is 12 but the search value is 17. So you'll simply say that since root value is lesser than the search value, I'll simply move towards the right. Fine. So that's how you can work in this case. So you'll simply say that if root value is lesser than the search value, so you will be moving towards the right. Okay, so you have successfully changed your pointers from left to right. Works like that. Now your value matches with the search value. What will happen? That means your root value matches with the search value. That means if you wanted to search for 9, suppose, okay, you will say that 9 is lesser than 12. That means we'll move towards the left side. 9 is greater than 7. That means we'll move towards the right side. 9 is equal to 9. That means we will now perform the delete operation. Okay, so now we are actually performing the delete operation. So this actually means root value is equal to search value, and this simply means we'll be moving search on right side. Okay, we'll be performing search on right side, and similarly we'll be performing search on left side. Okay, I hope you got this. So this is the initial step which we need to take always for searching anything. Okay, you are searching an element, and now what will happen is, I'll just say that if you want to move towards left side, your root will become left side of this value. Okay, that means root dot left will actually become the root value again. Okay, so you will be again calling this delete node function with the left value and the search value. That's it. Okay, fine. So what I'll do is I'll simply say just call this recursively root dot left. Okay, is simply, you'll simply perform the delete operation on the left side. Okay, so now this won't be affected, this won't be affected. Now delete operation will be performed on the left side of that root. Okay, so now we are performing delete operation on the left side, and similarly in this case we'll be performing delete operation on the right side. That's it. Okay, you can actually print values console.log to actually get what's actually happening on the left side. You can print these values what's actually happening in the right side. Okay, now you have reached your destination. This is actually for searching. Now you have reached your destination. So here comes the main part. Now your value, that is, you were actually searching for 5, that means this was 5, and now your pointer is at 5. Okay, we are shifting the pointer. In this case we are actually shifting the pointer, we are actually converting the root to root left, again root to root left, and similarly root to root right, root to root right. It's like that. Okay, so here what we'll do is, first case is what? Case 1, no child. Okay, so in case 1, no child, we'll simply return the value as null. That means whatever is the value, whatever will be the old value will be changed to null if it had no child. Okay, so I'll simply say that if my root does not have any child, okay, and that means either left side or right side, that means it's a leaf node. Okay, it's the leaf node, then I'll simply return null. Okay, this was the case 1. Okay, now we come to the case 2. We have one child, so what will happen to one child is actually you'll simply shift it upwards. Okay, you'll simply shift it upwards. So shifting upwards simply means in this case you can assume that if I have left child, I don't have right child. Okay, if I have right child, I don't have left child. So I can simply say if I don't have left child, okay, if I don't have left child, that means I have right child. Okay, so I can simply return the right side. Okay, simply return the right side. And similarly, if I have, make sure this is first. Okay, this is run first, because if I don't have any child, then we'll return null. If I have at least one child, either left or right, these will be the second cases. Okay, these will be the second cases. Okay, so what I'll do is I'll simply return the left side. Okay, simply return the left side. Whatever is the left subtree will be returned. Okay, so again the value will be taken by left subtree. Okay, so that's how you can perform the second case. Now comes the third case, very important. Okay, so third case is actually important because it's way more complex, and it's actually not complex that much. You'll simply find the minimum of right side. Okay, right side. So I'll simply say that if it had two childs, okay, if it had two child, so what I'll do is here you can simply pass the else case. Okay, and here you'll just say let minimum value is the right side. Okay, is the right side. Okay, whatever is in the right side of the minimum value of the right side. Okay, so I'll simply get the minimum value of the right side. That's it. Okay, now what I'll do is this function must be already created. You can see that we declared it right now. Okay, we declared it initially. Okay, so you can actually watch the video again so you can get how we created this function. Okay, so now we have the right minimum side, minimum tree. Okay, what will happen is, now what will happen is we have the minimum value, okay, of the right side, whatever is available in the tree. You can actually print this to get a more better idea. You can just console.log to get what's actually happening here. It will simply return the right tree. Okay, right tree. Okay, that means the right side and the minimum value of the right side, whatever is the minimum value of the right side. And in our case, suppose if I talk about somebody wants to delete 12, what will be the minimum value in the right side? Obviously 17, because it's only the one value available in the right side. 17 will take place of 12. That's it. Okay, so that's what happens here. It will simply return 17. Okay, it will simply return 17. Okay, that means I'll simply say my roots value will now become 17. That's it. Okay. Roots values will simply become 17. And now what will happen to the right side? Simply I'll again perform the delete operation. Okay. That means what will happen to 17? Okay. 17's old value, old position. 17 takes position of 12. What happens to 17's position? What happens to that? So I'll be simply performing delete operation, and here what I'll say, it start from the right root. That means the right root is can be anything, can be anything. You can assume it to be suppose 25 or something like that, and what you are trying to search for is 17. That means you want to delete 17 in the right subtree. Okay, you can assume it like that. Okay, so it works like that. So I'll just remove it again and I'll explain it with the whiteboard. So here you can see, suppose in this case you deleted 13. Okay, so again the operation will be actually like once you deleted 13, that means 13 took place of 12. Okay, 13 took place of 12. That means we have already done this. We have already done this. 13 took place of 12. Now what happens to value of 13? Value of 13, simply I'll call the right subtree, I'll call the root of right subtree, and I'll provide 13. Okay, I'll provide 13. That means I want to search for 13. 13 won't be removed first. First it will be copied to 12. First it's copied to 12. Then this tree, this right subtree will look for 13, will look for 13. 13 was actually here, so the pointer will stop here. Again delete operation will be performed, and it works like that in the tree recursively. Okay, so I hope you got this. Things are working like that. So again you have performed delete operation and you are looking for the value 13 and you are deleting 13 from the right subtree. Okay, I hope you got this. All right, so that's how actually things work in trees. And now what we'll do is we'll simply, yeah, we'll simply return root here. Yeah, we'll simply say that, yeah, return the root here. We have this else case. Okay, fine. Okay, fine. Let's see how it works. So what we'll do is, yeah, we are actually looking for the right side, left side, fine. So we'll be now simply returning the root. That means whatever is the root will be simply returned here. Okay, that means we can actually perform console log also. So if you want, you can see what's actually happening to the root. Okay, so now we'll be performing delete operation to this tree, to this tree. So you can see that we have inserted some values 12, 7, 17, 5, 9, and here I have actually called BFS order. In the last video you can check out BFS and DFS video to get the idea. Okay, so node script1.js, here you can see that this was the BFS operation. Okay, that means 12, 7, 17, 5, 9. we'll be actually using this to see what element is deleted. Okay, it actually tells me the order 12, 7, 17, 5, 9. It works like that. Okay, now suppose I want to delete an element. Suppose I want to delete 5 here. Okay, I want to delete 5 here. What will happen is, let's delete 5. So what will happen is 5 will be actually deleted, but we need to call it after this. Okay, we need to call it after this. So you can actually see 5 is sorry, we don't want to delete this. We actually want to delete. Have we committed any mistake here? Okay, let's see what mistake did we do. First, what I did was I simply made its value as null, root equals null. Okay, then what I did was, I'll just expand this. Then what I did was, first the value is null. Then what I did was, its value is greater than, okay, yeah, fine. Or if its value is lesser than, okay, fine. Okay, fine. Then in the else case, I simply said that if the left and right does not exist, simply return null. Okay, and if the left does not exist, return the right side. If the right does not exist, return the left side. And then after this, you can see that in the else case, it's actually if both of the childs are available, then we are simply returning the min value, and min value is simply equal to, I think there is some typo here. We'll see that what's the problem here. Okay, so let's write this again. So I'll just say root dot value equals minimum value of right. Whatever is the minimum value will be taken by this. And now we are again performing the delete operation on the right subtree. Again, the delete operation on the right subtree, same. And I think this is fine. Okay, let's see how it's working now. Okay, so now you can see I actually tried to perform the operation on 5, but it actually performed the operation on 17. Hmm. Okay, I think there might be some problem in this case also. So what I'll do is I'll simply say that if the value is lesser than root dot value or root dot data. I think this is root dot data which we are talking about. Yeah, it's actually root dot data. It was my mistake. So I'll just change root dot value wherever I have written root dot value first of all to root dot data. Okay, fine. Now we'll see. I think this will work, and root dot data is changed to everywhere. Okay, I think this will work. Root dot data. Fine. Let's see. So you can see now it works. Okay, 5 is actually removed. So order is like 12, 12, 7, 17, 9. Okay, so let's look into the tree. So you can simply say 12, 7, 17, and 9 is given. That means 5 is removed. 5 is removed. Okay, now if I talk about 7, I want to remove 7. What will happen to 7? Let's type 7. And now if I hit enter, you can see 12, 9, 17, 5. Okay, that means 12 and 9 will actually take place of 7. Why it's taking place of 7? Because 9 is minimum of right subtree of 7. Fine. So 9 takes place of 7. So 12, 9, 17, and then 5, and 9's value now becomes null. Okay, so it stops here. Okay, so it's 12, 9, 17, 5. Fine, it works like that. And suppose if I talk about 12, if I remove 12, what must happen here is, let's see. So here you can see now the root becomes 17. 17 is now the root. So what actually happen is if I remove 12, I'll be looking into the right side for the minimum value. Minimum value is 17. So 17 will be replaced by this. Now again the tree will actually become 17, 7, no value, null, okay, empty, 5, 9. So it's like 17, 7, 5 9, it's like that. Okay, so that's how you can perform delete operation in any of the tree. Okay, in any of the first binary search tree. Okay, binary search tree. So that's how you can perform delete option in binary search tree. And to see the value, to see the correct order, you can actually use this BFS order, breadth first search order, to get a better overview how elements are removed from the tree. Okay, you can actually do this again here. You can print a console.log, and I'll just say that we have some empty value here. Okay, so let's see. So you can see first the tree was like, okay, I'll just do this again. So here you can see first the tree was like this, and then after removal it was like this. Okay, so that's how you can play with this, and I hope you understood the delete operation in this video. Okay, so we have covered everything, and this was a complete delete operation. You can rewatch this video. If you have any doubts, you can ask me, and I would suggest that watch the 3 videos specially for the trees which I have covered in this playlist. So just visit the Geeks for Geeks practice channel, and it will take you to this page. Here you just need to look for the playlist section. Here you need to look for the data structures and data structures using JavaScript. Okay, so inside this you'll find introduction to tree and BST. Okay, and then we have operations in BST part 1, BFS and DFS, and then this is the current video part 2. So you need to look for these 4 videos so that you get a better idea. Okay, so I hope you understood this video. Before ending this session, in the live chat you'll find a link for a course provided by Geeks for Geeks, that's for data structures and algorithms. You will find the same link in the description. So if you want to learn data structures and algorithms in JavaScript, you can check out this course. This is a great course, and this is a paid course. Okay, so you can actually purchase this course. So if you want to know what are the contents of this course, so you can check out the content here. Okay, so everything required for becoming a developer, Excel developer, okay, complete powerful developer, you can actually learn DSA in JavaScript, because JavaScript with data structures and algorithm will actually give you efficient code. Okay, so you can check out this one, and everything is covered. So if you are thinking about that, what about competitive programming, so you can refer any other DSA material, you'll find the same topics. Okay, that means that it's actually available for, it's actually complete for competitive programming also. If you want to perform tasks on competitive programming, you'll perform programs on competitive programming. If the platform supports JavaScript, you can actually write DSA code in JavaScript, and you can write the code that way. Okay, so I hope you understood this video, and in the next video we'll be starting with some different topic. Okay, so that's it for today. I will see you in the next one. Till then, one more thing, if you have any doubts, you can message me on any of my live videos, or you can message me on Instagram also at the rate Harshal_3011, or LinkedIn Harshal Jain. Also, if you have any doubts regarding MongoDB, Node.js, React.js, Express, React Native, GitHub, AWS, Redux, Angular, Next.js, Firebase, C++, Python, C language, and recently I also learned GraphQL. So you have any doubts regarding that, you can ask me on any of my videos, or you can message me personally. Okay, so I hope you understood this video. I will see you in the next one. Till then, see you, a good day.